Computer vision is a really interesting problem and it's an important application of machine learning. Computer vision is the science of teaching computers how to see. When we say see, we actually mean that we want computers to be able to identify and extract information from images and videos. We basically want them to look at images and videos and be able to understand them, what those images or videos are saying, be able to describe them. And then they should be able to take decisions based on this information. This decision could be as simple as granting access based on recognizing somebody's face, or it could be something like a robot being able to take decisions based on what it can see. Let's look at some common tasks in computer vision. Handwriting recognition is a pretty common task. Given an image of a handwritten text, or if somebody is writing something down on a tablet, we should be able to convert it into text. As you can imagine, this could be a pretty difficult problem. Imagine deciphering a doctor's prescription, for example. Object recognition is another important task. Being able to look at a picture or a video, or looking out at whatever the computer can see right now and recognizing what images or what objects are there in that image. These pictures are a few examples of how a computer was able to identify objects in an image. For example, in the top left image, the computer is able to identify that there is a road, a car, a tree, a building, and sky. Similarly, on the bottom right, it's able to identify that some of the objects are persons and some are windows. Object recognition is a very important task in computer vision. Being able to identify the different objects and then put them together to describe the bigger picture is something that computers need to be able to do to move in the direction of artificial intelligence. Another interesting problem is face detection. This is slightly different and more difficult than object recognition itself, identifying a face in a picture and then identifying who that person is as well. Most cameras, whether they be DSLRs or even smartphone cameras, have this feature nowadays that they can identify a face and whether that face is smiling or not and snap a picture themselves. Another cool example of an application of face detection is Facebook's recent deep face algorithm, which is able to very accurately identify who a person in a picture is. The reason Facebook is able to do that is because of all the data that it has. It has a huge amount of data in the form of images posted by their users, and those images even have the tags of who are in the pictures as well. Computer vision, as you can see, opens up so many different possibilities. If computers could see and understand the world around them, they could do amazing things. For example, self-driving cars wouldn't be possible if you didn't have computer vision. The way self-driving cars are envisioned and the way they work today is by using a lot of different sensors and cameras around the car, which will feed in data to a computer, and then the computer tries to understand and process what are the different objects which are around it. If something comes onto the road, they have to slow down or swerve to avoid it. All of this is processed using computer vision techniques. So as you can see, there are a lot of interesting problems that come under the umbrella of computer vision. Some are very difficult to solve. There are no known solutions yet, and some have been solved. One of the starter problems that most people start with in computer vision is handwritten digit recognition. The idea is that you have a bunch of handwritten digits the digits can be between 0 to 9, and you need to identify which digit it is. So as you can see, handwriting varies from person to person. Each person would write 0 in a different way, 1 in a different way, 2 in a different way, and so on. Handwritten digit recognition becomes important when you look at applications like bank check processing. So if you wanted to automatically process a check at a bank, your program should be able to look a scanned image of a check and read the digits on it very, very accurately. Imagine the ruckus if the program read a 0 as a 9 or vice versa. So this is a problem that people have been trying to solve for many, many decades, in fact. There are many, many different proposed solutions with varying degrees of accuracy. But at the heart, all of these different proposed solutions are basically different approaches to solving a classification problem. So you take this problem and you look at it as a classification problem. Given an image of a handwritten digit, you need to classify as one of the digits between 0 to 9. There are standard image processing techniques that can take an image of a number and then break it up into the individual digits. Then, given each of those digits, you need to be able to classify it as one of the digits between 0 to 9. So whenever people come up with a new algorithm or an approach to solve this particular problem, they test the performance of their algorithm on a standard database. NIST is one such standard database of handwritten digit images. This database was created and is still maintained by one of the foremost researchers on neural networks and computer vision. And this database has about 60,000 different images of digits. And these digits have been written by 500 different writers. Each of these images comes with the correct label, whether it's which digit it is between 0 to 9. Another set of 10,000 images is provided so that people can test the performance of the algorithm that they've come up with. So use the 60,000 images to train your classifier and then test it on another set of 10,000 images. This is a standard process that most people follow when they're coming up with a new approach for classifying handwritten digits. So let's look at what are the basic steps involved in any classification problem. First, you will represent each of the data points in your training set, each image in the training set, as a feature vector, which is a tuple of numbers. So each image needs to be taken and converted to a tuple of numbers that represent that image. Then you would feed all these feature vectors along with the labels, which digit it is, 0 or 1 or 2 or 9. And you would take this data and feed it to a classification algorithm. The classification algorithm will learn from the training data what is the relationship between the features and the label. Then when you give it a new image, it will be able to look at the features of that particular image and say which digit it is between 0 to 9. So let's go through this step by step. First, we'll look at how an image can be represented as a tuple of numbers, and then we'll see which classification algorithm that tuple of numbers should be fed into. So the first problem is this: how do you take an image of a cat or a dog or a digit and then represent it as a tuple of numbers? The basic idea is that every image is made up of pixels. Most people would know the specs of the camera that they're using, whether it's a smartphone camera or a DSLR camera. You would say something like the camera has the ability to take pictures of 8 megapixels or something like that. This means that each picture that camera takes is made up of 8 million pixels. Take any image, and if you zoom in far enough, you will be able to see that it's actually made of a large number of tiny squares. And when you zoom out, at some point you will be unable to distinguish between the edges of the, and you'll see a smooth image. Here is one example of a handwritten digit 0 and the pixels that make up that picture. One tiny square that makes up this picture is called a pixel. Each pixel in the image can be represented by a tuple of numbers. The first number is the x coordinate of the pixel. This is how far away it is, say, from the left edge. The second number is the y coordinate of the pixel. This is, say, how far away it is from the bottom edge. Then you have the color of the pixel. If your picture is just black and white, that is, each pixel can take either a black color or a white color, then this color could be represented by a bit. Either it is 0 or 1. So it's a binary number. These three numbers together could represent a pixel, and all the pixels together could represent an image. Usually the color value won't be binary though. In fact, it would be a number between 0 and 1, and in that case you would see something called a grayscale image. That number between 0 and 1 would represent how gray that particular pixel is. 0 could be white and 1 could be black, or the other way around. What happens when you have a full color image? Each pixel then actually has 3 numbers to represent the color. Each number represents the intensity of one primary color. This could be red or green or blue. So each color then becomes a tuple of 3 numbers itself. Sometimes you might even have another parameter called alpha, which represents the transparency of that particular pixel. So this 3 or 4 number tuple represents a color in a full color image. The number of colors required to represent the actual color of the pixel, in this case it's 3, in grayscale it's 1. This number of colors is also known as the number of channels required to represent a pixel. Alright, we'll concentrate for a time on the grayscale images, basically where just one number is required to represent the color of the pixel. So if you are given a grayscale image, you can just represent it as a two-dimensional array. Each number in the array represents one pixel, its position in the image, and the value of the number represents the grayness or the color of that particular pixel. The size of this array would be the same as the size of the image. So let's say you have an image which is 100 pixels wide and 128 pixels high. Then that image could be represented by a two-dimensional array which has 128 rows and 100 columns. Each number in that array represents a pixel and the gray value of that pixel. Now, this two-dimensional array could actually be used directly as a feature vector for a classification algorithm, because you've already represented the image using numbers. However, if your image is full color and it has millions of pixels, then this feature vector could end up having too many dimensions. It could be that some of these dimensions are just redundant. There is not too much information that you get by having them. For example, you could blur an image to quite a large extent and still be able to make out what that image is representing. You could represent an image using a much smaller number of pixels, and you would be looking at a blurry image but still be able to make out what that image is. The idea here is to perform dimensionality reduction, to identify just the right set of features that will help us identify which image it is without having to process the image represented by all the pixels in the image. Feature extraction techniques can help us find a small number of features that can represent the image. there are many different feature extraction techniques for images. Some of them will help you find the edges and just represent an image using the edges of that image. Some of them will compress an image into a blurry but still recognizable version of that image. In fact, in recent times, people have used unsupervised feature learning techniques as well, where they allow a learning algorithm to identify the features by itself that really represent an image. The idea with unsupervised feature learning is that if computers or programs can identify the relevant features in an image by themselves, these could be edges. For human faces, this could be like the nose, the eyes, and the ears, and so on. If they can identify these features by themselves, then they are closer to being independent or closer to artificial intelligence. Let's quickly look at one very simple method that we could use to reduce the number of dimensions required to represent an image. We could divide the image into a number of zones of equal size. So let's say we have a 6 by 6 image here. There are 36 pixels in this image. We divided it into 4 zones, each of 3 by 3. Each has 9 pixels in it. Then within each zone, we could count the number of black pixels. Here, black is represented by 1 and white by 0. So the top left zone has 3 black pixels, the next one has 3, the bottom left has 4, and the bottom right has 4. Now, instead of representing this particular image by 6 by 6, that's 36 numbers, you could represent the same image using these 4 numbers, 3, 3, 4, 4. So this tuple of 4 numbers could be used to represent the image instead of using the entire 36 number tuple. So we have reduced the number of dimensions from 36 to 4. This is one very simple but crude way of extracting features from images. It's called multi-zoning and it is actually used pretty commonly. Okay, going back to our digit recognition problem, we've walked through the first step, which is how to identify the feature vector, how to represent each image as a tuple of numbers. Let's now walk through what are the choices for different classification algorithms that we can use, and one particular algorithm called deep learning networks. We'll do that in the next class.